There is a moon in our solar system where the conditions for life may exist right now. Not on Mars, where we have spent decades searching. Not on some distant exoplanet, light years out of reach. Closer than that. Orbiting Saturn, more than 1 billion kilometers from where you are sitting, there is a small, icy world. And what we have learned about it in the last 20 years has changed where we look when we ask whether we are alone. It is now one of the most important targets in the search for life beyond Earth. We have not found anything yet, but the more we have learned about it, the harder it has become to ignore. This is the story of Enceladus, and of what may be hiding beneath its ice. Enceladus is small, only about 500 kilometers or 310 miles across. You could fit it inside the British Isles with room to spare. It moves in a slow orbit through the cold outer reaches of the solar system, more than 1 billion kilometers from the Sun, where temperatures on the surface fall to around -201 degrees Celsius or -330 Fahrenheit. Its surface is one of the brightest in the entire solar system. About 80% of the sunlight that falls on it bounces back into space, giving the Moon the appearance of a polished sphere of fresh snow. For 2 centuries after its discovery, astronomers assumed Enceladus was inactive, a frozen, geologically silent ball of ice drifting alongside the other moons of Saturn. There was no reason to think otherwise. Then NASA and the European Space Agency sent Cassini, a spacecraft the size of a small bus, designed to spend years in orbit around Saturn. Cassini arrived in the Saturn system in 2004. In 2005, it began making close passes near Enceladus. What it found did not match anything anyone had predicted. As Cassini approached the Moon, the magnetic environment around Enceladus behaved strangely. Saturn's magnetic field appeared to be deflected, as if it were running into something invisible just above the Moon's southern hemisphere. When the imaging team turned the cameras to the South Pole, they understood why. Towering above the icy surface, rising hundreds of kilometers into space, was a curtain of geyser plumes. Jets of water vapor and ice particles erupting from cracks in the Moon's surface and shooting into the vacuum at speeds of more than 400 meters per second, or around 900 miles per hour. The plumes were coming from a region of the South Polar terrain that scientists now call the Tiger Stripes. 4 roughly parallel fractures, each around 130 kilometers long, that look on the surface like dark scars across the white ice. Below those fractures, something was forcing material out into space. Some of that material fell back to the Moon's surface, but much of it escaped Enceladus's gravity entirely and drifted outward into orbit around Saturn itself, where it joined a vast, diffuse ring of ice grains that traces the exact orbit of Enceladus around its parent planet. Saturn's E-ring, invisible to the naked eye and about the width of Saturn itself, turned out to be fed by Enceladus. This small icy moon was not just active, it was quietly building an entire ring of the giant planet it circled. A small icy moon in the outer solar system was somehow producing enough internal heat to keep liquid water erupting from its surface at rates high enough to fill a ring larger than most planets. In 2005, this was not supposed to be possible. Over the following years, Cassini flew directly through those plumes and sampled what was in them. The composition told a story nobody had anticipated. By 2014, gravity measurements from Cassini's close flybys had revealed a large subsurface ocean beneath Enceladus's south polar region. A year later, measurements of the Moon's slight wobble as it orbited Saturn showed that this ocean was not just regional, but global. A worldwide ocean of liquid water, wrapping around the moon's rocky core, beneath an ice shell that may be only 1 to 5 kilometers thick at the South Pole, and roughly 20 to 25 kilometers thick on average elsewhere. The ocean is estimated to be between 26 and 31 kilometers deep, roughly 16 to 19 miles. That is more than twice the depth of any ocean on Earth, and it has been there probably for hundreds of millions of years. How can this be? Enceladus is small. It orbits far from the sun's warmth. By any conventional thermodynamic accounting, it should have frozen solid billions of years ago. The answer lies in Saturn's gravity. Enceladus moves in a slightly elongated path that brings it closer to Saturn and then farther away. As it does, the planet's tidal pull stretches and squeezes the moon's interior. That continuous flexing produces friction. The friction produces heat. And the heat, generation after generation, has kept the water beneath the ice from ever fully freezing. The same gravitational mechanism that keeps Jupiter's moon Io volcanically active has shaped Enceladus into something very different. The fact that there is liquid water beneath Enceladus's ice is not, by itself, what makes the moon interesting for the question of life. What makes Enceladus interesting is what is in that water. Cassini flew through the plumes on multiple occasions during its years at Saturn. The most extreme of those passes came in October of 2008, when the spacecraft threaded straight through the icy spray at 18 kilometers per second, roughly 40,000 miles per hour. Pristine grains, ejected from the moon's surface only minutes before, slammed into Cassini's dust-analyzing instrument at that velocity. Nobody at the time realized how much the speed of that impact would end up mattering. The years of analysis that followed transformed our understanding of what is happening beneath the ice. In 2017, scientists reported the detection of molecular hydrogen in the plume material, in concentrations high enough to indicate that it was being actively produced inside the moon at the present day. On Earth, hydrogen of that kind is produced when seawater reacts chemically with hot rock at the ocean floor. At hydrothermal vents in the deep ocean, hot mineral-rich water from the planet's interior meets the cold seawater above, and hydrogen is released as a byproduct. The hydrogen detection at Enceladus suggested that the same process was happening on the floor of its hidden ocean. Hot water, in contact with rock, releasing hydrogen into the surrounding sea. The discoveries kept coming. In 2021, scientists reported that methane in the plumes was difficult to explain with the non-biological chemistry they modeled. On Earth, much of the methane in our oceans is produced by microorganisms living near hydrothermal vents. On Enceladus, the methane could still have a non-biological source. But the amount detected is difficult to explain with the abiotic processes tested so far, which keeps biological methanogenesis on the list of possibilities. In 2023, a paper published in Nature reported the detection of phosphates in the plume material in concentrations far higher than in any seawater on Earth. Phosphorus is one of the 6 elements that all known life requires. And then, in October of 2025, scientists returned to the data from that 2008 fly-through with new analytical techniques. What they found had been hiding in the archive for nearly 2 decades. At the extreme speed of the 2008 pass, water molecules in the impacting ice grains had not clustered together the way they do at slower impact speeds. And in the space those water molecules would ordinarily fill, previously invisible signals emerged. Specific classes of organic molecules never before detected in ice from any world beyond Earth. Aliphatic compounds, cyclic esters and alkenes. ethers. Tentatively, molecules bearing nitrogen and oxygen. On Earth, these are the intermediate steps in the long chemical chains that build up toward the more complex molecules essential for life. Some of the same molecules had already been found drifting in the E-ring, the ring of aged Enceladus grains around Saturn. But those grains were sometimes hundreds of years old, weathered by radiation, chemically altered over time. Finding the same molecules in fresh grains captured minutes after ejection confirmed that this chemistry is being produced right now, inside the Moon, and released into space along with the water and the salt and the hydrogen and the methane. What Cassini had been tasting in those plumes turned out to be a list of the conditions, and now the ingredients, that on our own planet are associated with the deep origins of biology. On Earth, there is a serious scientific argument that life began at hydrothermal vents on the floor of the early ocean. The gradients of heat, the constant flow of energy from the planet's interior, the chemistry of hot, mineral-rich water meeting the cold sea above, may have been the cradle in which the first self-replicating molecules formed nearly 4 billion years ago. Whether that hypothesis is fully correct or not, the deep vents of Earth's ocean are now home to entire ecosystems of microorganisms that live entirely on chemical energy. No sunlight, no surface. Just the chemistry of the rocks and the water around them, in complete darkness, sometimes for millions of generations. Enceladus appears to have, beneath its ice, the same kind of environment that those Earth ecosystems require. Liquid water in contact with hot rock, hydrogen as a chemical fuel, phosphates and organic carbon, methane in concentrations that suggest something interesting is happening in the chemistry of the deep ocean. This does not mean there is life on Enceladus. We have not found life there. We have not even seen the floor of the ocean. What we have found is a place where the conditions match what we know about the origins of life on Earth, and where the chemistry of the plumes does not yet have an obvious non-biological explanation for everything we are seeing. Imagine descending through that ice. You would fall for several kilometers through frozen water so cold and so ancient that it would look almost blue-black in the darkness. Chambers of crystalline ice, pressed together over millions of years. And then, without warning, you would come out into the ocean itself. The ocean would be lightless. No sunlight has ever reached it. But it would not be still. Down on the sea floor, more than 20 kilometers below the ice, warm water would be rising from cracks in the rock. Cold water would be sinking to meet it. Where the two met, hydrogen would be released, methane would rise, phosphates would settle out in the mineral seams around the vents. And around each of those meeting points, the chemistry would be almost exactly what it needs to be for something living, if something lived there, to survive. We do not know what is down there. That has been the whole story since 2005. Everything Cassini measured pushed us closer to the question without ever quite answering it. The spacecraft ended its own mission in 2017, deliberately burning up in Saturn's atmosphere so that it could never fall onto Enceladus and contaminate whatever might be there. No spacecraft has visited Saturn since. Mission concepts to return have been proposed, and one of them may eventually fly. But even if a future spacecraft eventually reaches Enceladus and finds no biological signal in the plumes, the ocean will still be there, unread. The chemistry will still be running, generation after generation. Whatever does or does not live in that dark hundreds of millions of years deep will not stop because we happened to look and see nothing on the surface. For now, Enceladus is a small bright moon throwing curtains of vapor into the dark above Saturn's rings, as it has probably been doing for far longer than there has been anyone on Earth watching. Every few days, its geysers exhale a fresh sample of the ocean into space. Every few decades, we get slightly better at reading what those samples say. Someday, if we are both patient and lucky, we may know. Until then, the question stays open. And of every place in our solar system we have ever looked, this is the one that has kept its answer to itself the longest.